Good morning. Good morning, you. Can you hear me?
Yes, sir. Good morning.
Good morning. So today's topic is the last topic of the unit one, that applications in space technology, cryogenic applications in space technology, application in space technology of cryogenics. So we have already discussed on the basics of cryogenics and the various examples for the cryogenics also discussed, like liquid oxygen, liquid hydrogen, liquid nitrogen, and liquid helium gases and their properties, mechanical, physical, and electromagnetic properties are already discussed. Other than that, we were discussing on how to handle the cryogenics and storing as well as transportation of these cryogenics. Safety related to that topic, everything was discussed in the last classes. So the last topic related to this unit one is applications in the space technology, that cryogenics application in space technologies. So start with the applications. As you know already, it was well known to us, like cryogenics are nothing but they are the fuels in the form of liquid. If we are supposed to maintain extremely low temperature to maintain them in the liquid state, it can be generated from the distillation of the air or gases, gas separation plant or air distillation plant. From the distillation plant, it will be liquefied and purified and processing. After that, we will be able to get the cryogenic fuel in the form of cryogenic liquid. So the maintain very important part is extreme lower temperature to maintain them in the liquid state. There is a difference between the storable propellants and these cryogenic propellants. So cryogenic fuel most often constitute liquefied gases such as liquid hydrogen, liquid oxygen, liquid nitrogen, liquid natural gases, and liquid methane and liquid helium. So mostly the cryogenics in the application of the space technology is mostly on space missions. Normally, that will be fall into two categories or two broad areas of applications. One is for supporting the space missions, science missions, and other one is for supporting the space transportation infrastructures. So one way of application is space science missions. Other way of this cryogenic application is space transportation infrastructure. So we are going to discuss one by one this forthcoming slides. So normally, if you coming to the point of application on the science application or the space science applications, as was given in the first mission, the space science missions. So coming to the third category, space science application or missions. So many science or space science missions are use infrared or gamma rays or X-ray rays or detectors. So that has to be operated at very extreme load, otherwise too it will be get heated up. So there has to be cooled down by using this in the form of cryogenic temperatures. It should be lower temperatures. So for that it will be used applicable. So the detectors are what is meant for detection is meant for the missions infrared and gamma rays and X-ray rays. That has to be cooled down by using the cryogenic temperatures. Then so that sensitivity will be increased. So the detectors are cooled to increase their sensitivities. Not only like that, the telescopes. We are using the telescopes in astronomy missions and all. There will be some thermal emissions, so that then only we can able to see the objects to be seen very clearly. That for that purpose we go to cool down the telescopes. The telescopes are used cryogenic telescopes. So this for supporting all these kind of space missions or science missions, a broad range of cryogenic technology is employed. Such that they will meant for the properties related to the property of the strength, dimension, thermal, electrical, magnetic, and optical properties that has to be controlled. So that we can able to visible by using these telescopes or optical properties has to be changed. Similarly, for other field like magnetic, electrical, thermal, and other dimensional strength of these materials has to be taken account in this application of the cryogenic technology. So the purpose of the cryogenic system is to thermal emission and heat generation has to be controlled. Detection using some rays, gamma ray, X-ray, and other rays. So that has to be controlled by maintained by using extremely low temperatures. For that, we are using this cryogenic liquids or cryogenics for this application, and especially in the science space missions. So that coming to this telescope part, so that is very important. We have to design a telescope. It should be assembled in a room temperature. That should be cooled to 20 Kelvin, around minus 50 degrees C, so that it can launch into the space. And also, that's why due to the vibration environment and the changes when dimension changes will occur, cooling down, the instrument must to be in focus and provide undistorted images. So optical parameters. So that has to be all should be well insulated, having very low masses. So that has to be taken into account in these space science applications related to the telescope usage on the cryogenic telescope usage in the application of space missions. Then there will be some radiators. Also, not only the telescopes, apart from the telescope, then first one detectors, second one is telescope, third one is radiators. So radiators is not normally, radiators meant for cooling purpose. It can cool the instruments to 100 Kelvin in Earth orbit. So that radiators are nothing but blackened surfaces shielded from the sun and earth. That is known as radiators. That is meant for cooling the system in orbits far from the Earth orbit, such as special usages, there will be some temperature should be in the range of 30 Kelvin. The previous one, the instruments can be in the 100 Kelvin temperatures. If you want to below the lower temperature of 30 Kelvin system, so for these lowest temperature instrument systems, we have to use stored cryogens such as nitrogen, neon, or hydrogen as a solid cryogens. So it is will work for the environment requirement to down the temperature from 100 to 20, 30 to 6 Kelvin, the range, very, very low temperatures. For these lower temperatures, liquid helium can be used in the range if it is the range of 1 to Kelvin ranges. So all these cryogenic system or cooling systems can be used as the cryogens can be used in the form of cooling area with respect to thermal detectors or maybe in the kinds of that telescope system, cryogenic telescopes, or maybe in the radiator systems. So containing liquids while vending the different effect has been a challenge. But only the problem, if we want to maintain 1 to 12 in range of temperatures by using a liquid helium for attaining this lower temperature of instruments for the purpose of radiating instruments, there we have the only challenge is we go to vending of the effluent vapor or exhausting vapor or liberating vapor has been a very important challenge compared to this use of this instruments with lower temperatures and radiators and all. So cryogen is always consumed in always ending with the missions. So there will be some advances they developed with the closed cycle refrigerators for applications. So if it is the open cycle, so that will be consumed to everything is consumed. That cannot be used again. So ending at the end of the mission, that propellant, sorry, the cryogenic fluids may not be available. It will be fully consumed. So recently there will be some development with the closed cycle. They are reused again by using the cycle by having the closed cycle refrigerators for applications. So it is also a coolant as a cryogenic refrigerators against a cryogenic low temperature system. So these coolers can be extended. This is called as the coolers or refrigerators in the form of coolers can be extended the mission duration. The temperature may be in the range of very, very low, in the range of 0.05 Kelvin. So these coolers have long life. We have to use these coolers for a long period of time. The area of a year of 5 to 10 years. So to have a very low mass, that we already have solar cells and electronics for the coolers ready to reject heat, and also to have very low vibrations. So this is related to the coolers that we are using in the form of the closed cycle refrigeration systems, so that all the cryogen may not be consumed fully at the ending of the mission. That will be reused again, as well as the temperature range is very, very low of 0.05 Kelvin, and the duration of this usage of these coolers may be in the range of 5 to 10 years. As well as it have a very low mass system, as well as it have very, very low vibrations. So another area of space science is cryogenics is sample preservation. So we are supposed to preserve something, materials, preservation of the samples. So for an example, if you are using some biological samples in the space shuttle or the other comets, asteroids, and other planets, so we got to preserve the material. We got to use the biological samples, or we got to use the preservation of the materials that will be gathered from these applications like planets and asteroids and comets. So that sample has to be preserved. For this application also, these cryogenic fluids can be used. So this application have used phase change materials, solid to liquid or transition or liquid nitrogen absorbed in a fine porous coolants. So this is a phase change applications. This application can be used as phase change material of phase materials, change of phase of materials, the preservation process. So here also we can use the closed cycle coolers that can be used to store or preserve the materials either from these planets or cosmets or asteroids, so comets or asteroids, as well as the biological samples. So this is also one of the another usage of cryogenics in with respect to the space application of the space science missions. So these are all the discussion coming under space science missions. So not only other than that, as we discussed, as I told earlier, there are two broad areas of these applications. One is supporting the space science missions. Other one is for supporting the space transportation infrastructure. So that so far we are discussing on space science mission that started with the space science mission application of liquid helium, liquid nitrogen, liquid helium, liquid hydrogen, liquid nitrogen, liquid nitrified LNG gases. All these can be used. That can be used in various ways of space science missions. That one of the mission is the detector, thermal detectors. The other one is the coolers. The other one is the form of refrigeration system. Other one is in the form of the using the telescope systems. So that are all the applications. The coming to the detectors, already we are discussing. The detectors mainly used gamma rays, X-rays, and other rays. There will be some extreme. There may be some temperature generation or liberation takes place. That has to be cooled down. The detectors are cooling down. For that purpose, we are using this. What is that? Um, the cryogenic, so that the sensitivity of the material instrument has to be increased. So not only with respect to detectors, other than detectors, the cryogenic telescope can be used. The optical parameters has to be enhanced, or there will be some emission of thermal energy. So it can't be able to see the proper image of the object. So that will be taken into account, as well as not only that one, electrical magnetic property of this entire system also has to be taken into account. For that, we go to cool down by using these cryogenic liquids. So the range of temperature is 20 Kelvin. It will be has to be vibration removed one that case. So other than the detectors and telescopes, one more is the radiators. So radiators, there we have 100 Kelvin to point. We can have 1 to 2 Kelvin range of application also with respect by using some liquid helium. If you are using solid hydrogen cryogens or solid hydrogen system, nitrogen, helium, or hydrogen, that we can achieve 6 Kelvin range of temperatures can be used for this cooling the instruments. So apart from that, that it has to be consumed. So we got to avoid this consumption of this cryogenic fluid. For that, we got to use some closed cycle refrigerant systems to cool down the range of 0.05 Kelvin, very extreme low temperatures, and the life has to be maintained, increased, so that it can be operate during a duration of 5 to 10 years. So there's the system have the very low masses and have our very low vibrations. Another application is now we have the preservation. Preservation correspond to the these material gathering from these application planets, comets, and asteroids, or all in from these biological samples that can be preserved for a duration. So for that we can use some coolants. So that coolants can be used for preservation of the sample, some materials or samples, biological samples and all. For that we can use cryogenic coolers, closed cycle coolers. It should be a closed cycle cooler so that it can maintain or you can preserve the material with proper temperature and maintain its property remains same. So that are all about the that application of the cryogenics with respect to the space science missions. The second broad area is this space transportation applications. Are you there? Can you hear me?
Yes, sir.
Do you have any idea, any doubt with respect to the space missions?
No, sir.
No. Okay. So let me continue with the next topic, next area of applications. That is space transportation. So as we know, we have all the properties of these liquid cryogenic fluids, boiling point, critical point, and all. So that we already discussed, triple point, all these things we discussed earlier. So with respect to the boiling point only, we are maintaining the temperature of the particular system of operations. So we are coming to the transportations, space transportation, especially in the space shuttles. So we can use liquid hydrogen and liquid oxygen. There will normal boiling of the boiling point of the range of 20 Kelvin and 90 Kelvin. So this can be used in space shuttle as a space transportation applications. So for these applications, are using the propellant in the space shuttle, they have to store in the poorly insulated external tank. So that we want to go for there we want to improve the storage time of the propellants to a few hours of usage, so that you got to supply, then it can be used to able to resupply rockets with this propellant from depots in space. So for this principle, we have that it is discussed above that there we have to use the size of transport systems and many tons of propellants with using very new engineering approaches to maintain them this in for transportation during transportation, since we are using a poorly insulated external tank. So that has to be improvement. Design has to be enhanced. The size of the system has to be enhanced, and a ton of propellant has to be used, and that has to be cooled down with proper temperatures. So that has to be taken into account. Very important point we got to take into account for this space transportation application. In rocket engine applications, so we can use, as you know, most of the cryogenic rocket engines or liquid propellant cryogenic engines are powered by using cryogenic propellants. They may be, we can use liquid hydrogen or liquid natural gases or liquid methane or liquid nitrogen, liquid fluorine. All these liquefied gases can be used as the fuel. Other one of your oxidizer and other nitrogen will be can be used as the oxidizers. So that part we are using already. We know the heating due to the heat generation or the combustion of the fuels using it there. Then we have to cool down the system. For that, we are using a system adapted system known as a regenerative cooling. So what is the thing is we are circulating the cryogenic fuel around the nozzles before the fuel is pumped into the chamber and ignited. So that is the system we are using. That is called as regenerative cooling. So the cryogenic fuel we are already using, that is meant for combustion of these as in the form of propellant, fuel and oxidizer. Then after that, it has to be changed into, then we got to cool down the hot gases around the nozzle exit. So that has to be avoided by providing the cryogenic fuel around the nozzle, so that it can be cooled down. The hot gases coming out of this nozzle system will be cooled down. The nozzle surface will be cooled down, so that we can maintain the temperature properly. Then we can allowing the fuel and oxidizer in such required manner in the chamber, and it can get ignite. So that is the application correspond with respect to the rockets applications. Similarly, already we have discussed detectors, telescopes, and clue probes, etc. So that are all the infrared sensors or cooling of the sensors also very important, so that the sensitivity also system is used. So that is also application with respect to the space technology. So development of, we are developing some small cryocoolers that can be used for satellites for improving accuracy and reliability on Earth observation. So if you want to launch a satellite or a space application transporting missions, there if you want to increase the accuracy and reliability of Earth observation, so we go to develop some small cryocoolers or miniature type of the cryocoolers that can be used for in the field of satellites. There also we can use this cryogenic cryocooling system with the low temperature, extreme low temperature maintenance, so that this thermal emission can be controlled during this operation of the satellites. So already we have discussed space coolers. So here also coolers can be, it can be a cold heat sink. We can say we have hot sink and cold sink, since the coolers are having the low temperature system. So it have cold heat sink. So that what we are doing is we are removing the heat from the cold area and dissipating into the warm area. So this via radiator, sometimes the energy is directly radiated to space through radiators, or work has to be performed by pumping energy between two temperature levels from a hole to home level. So we can easily radiating the system so that it will be cooled down. Such an open system, the same thing can be used in open cycle refrigeration in a closed cycle. What we discussed in the space size missions. Here also space coolers can be used in the form of application with respect to the space transportation. So as I already discussed, if you are using the open cycle systems, the use of the stored cryogen is very difficult. So we can't use it. It has to be liquefied properly. Then it can be used. It will be fully consumed. So that will be some evaporation of liquid or solid cryogens takes place. So the cryo cycle having mechanical coolers, so it will be continuously cooling down during continuous operations. So this, for an example, if you are using 1 watts of cooling power in the temperature range of 50 to 100 Kelvin, using some Stirling coolers or positive coolers, we will discussing the types of cryo coolers in the forthcoming topics. So if in the range of 100 milliwatts, so we got to go for 15 to 20 Kelvin, very low temperature. It is using the double stage Stirling system. Or if you for a very few milliwatts, then temperature range is very, very low. It is known as, it is a 4 Kelvin. That is Joule Thomson temperatures that we'll discuss Joule Thomson effect and all in the next classes, next topics. So this is the idea behind that, how to maintain the temperature to generate this cooling power. So if you go for 1 watts cooling power, the range will be 50 to 100. If you go for 100 milliwatts, that should be lower than that, 15 to 20 Kelvin. Sorry. And if you go for a very few milliwatts, maybe the 4 Kelvin, that we would go for very low temperature 4 Kelvins. So if you are using very low temperature, there we have 3 helium absorption refrigerators. Cryosorption absorption refrigerators can be used. And the Procure system use temperature in the range of 50 millikelvin and 1 Kelvin also. So that can be, we can maintain very low, extreme low temperature in the range of 50 millikelvins to 1 Kelvin also. Very, very low temperatures. For base temperature above 5, you would use a single stage. So if you use the 3 stages, we go for multi stages, we can achieve this. The cryo cooling system with 3 stages, cryo cooler system with 3 stages, cryo absorption systems can be used to generate very, very extreme low temperature below the range of 1 Kelvin also. So this can be used for these space applications. Apart from that, transportation and these missions, we can have the space simulation can be one of the application of the cryogenic systems. These simulation chambers are realistic in the environmental spacecrafts. So we can use the space is simulated by using a liquid nitrogen cryogens. The level of vacuum required. If you want to make you find out the space simulation, that cryocoolers level of vacuum required for this system is should be very high. For that, you are using a cryo pump or turbo molecular pumps. So that also we will be discussing in future with the what are the cryogenic system, how the pumping will occur to pump the maintain or generate the very extreme lower temperatures. So these are all the very important applications of these cryogens, especially in the area of space technology. Other than space technology, this cryogens can be used in various applications. Medical field also they are using, on chemical plants they are using, and other industries also they are using. The purpose of cryogens is used to make, main purpose is used for uh, cooling, providing the cooling or extremely lower temperature systems of any operating areas. So that is